Anytime we're talking about acid-base reactions, we're talking about reactions that take place in solution. And so we're dealing with solutions, got to be dealing with molarity, dealing with concentrations. So we all know, hopefully by now, that molarity is moles of solute over liters of solution. And because everything with reactions comes down to moles, hopefully we know that. Grams don't react with grams. Moles react with moles. And so we need to know, and actually it really helps us in doing these sort of reactions. Molarity is basically a really nice shortcut to trying to figure out what's happening in a reaction and be able to calculate very simply what the concentrations of things are, what volumes of different solutions will be required, because we don't have to go back to working out like grams and moles. That's all been done for us. We automatically know how many moles are in a certain volume. And so we don't have to, the calculations become much, much easier. So it's a solution stoichiometry problem. All these questions are going to be solution stoichiometry problems. And I know how you all love stoichiometry as much as I do. All it is just quantities of chemicals taking place in reactions. These in particular are taking place in solutions, hence the very dramatic term solution stoichiometry. And it's the same strategy as we've used all along. We start out with, let me allow my annotation to get going here. We start out with a mass of something, some reactant. It's in some volume. And so from there, we figure out, based on the molar mass, what the molarity is. That gives us moles of reactant A. Then either we have reactant B or product B. Being that we know what the moles of A are, and where do we get the mole to mole ratio from? Where does it, we're going to find that out? Anyone tell me that? How do we figure out what the mole to mole ratio is between A and B?
The balanced chemical equation.
Oh, yes, of course. Excellent. Yeah, we need to have a balanced chemical equation. We can't really do anything without a balanced chemical equation. So like today, that's something we're going to have to figure out. We're going to have to figure out what is the balanced chemical equation, how many moles of base react with how many moles of acid, and figure out what that ratio is. Because now that we have moles of A, we can then go back and figure out what moles of B. And that's exactly what we're doing with our titration today. A titration is simply a way of measuring the concentration of an unknown because you have a concentration of a known. And if you know what the mole to mole ratio is between the unknown and the known, if you know the concentration of the known, and you should, it's known, right? If you know the concentration of A, you can figure out the concentration of B. That's exactly what a titration does for us. Oop. Here we go. So let's use that to figure out, we'll just do a quick calculation. This is exactly the sort of calculation you're going to be doing this afternoon and later on in your report. So I've got a bad tummy. So every once in a while I get an upset stomach and I take a tablet with hydroxide in it, generally calcium hydroxide or magnesium hydroxide, something like that. And what it does is that it neutralizes some of the stomach acid. That's right, thanks, Roger. It neutralizes some of the stomach acid. So the question is, how much, if I took one tablet containing 100 milligrams of magnesium hydroxide, how much stomach acid would that react with and neutralize? And inside your stomach, the concentration of hydrochloric acid is around 1/10 molar. So how do we go about solving this problem? So first, we need to write a balanced equation. We need to know we have a known amount, right? We have a known amount of something. The known amount of something we have is the 100 milligrams of magnesium hydroxide. But as I keep yelling over and over again. Grams don't react with grams. Moles react with moles. So we need to figure out how many moles that is. Next, we need a balanced equation to figure out what's the reaction between HCl and MgOH2. Then we use the mole ratio to determine if I have this many moles of the base, the hydroxide, how many moles of acid are going to be reacted with. So let's go ahead and do that, shall we? So here we go. So we've got 1/10 molar HCl. We want to know what volume of that is going to be neutralized by 100 milligrams of magnesium hydroxide. So what's the very first thing we have to do to solve this problem? So I've got 0.1 grams magnesium hydroxide. What's the very first thing I need to do after? This is basically the only information I have. So what do I do with that information?
We can calculate the mole of the 0.1 gram.
Exactly. We need to figure out how many moles that is. So we need to do, oh boy, a unit conversion. I know everyone loves unit conversion. So remember, with unit conversions, I don't want grams, I want moles. So we're going to put moles on top, and I'm going to put grams on the bottom. So what do I put for grams on the bottom? What goes there? What number?
Mass of magnesium hydroxide.
Right, the molar mass of magnesium hydroxide. So what is that? If someone can look that up for me. And remember, you don't have to get a periodic table and calculate it out. You can just Google mass MgOH2 and boom, you get the answer right there. Didn't have that when I was a boy. Had to look things up.
58.3197.
58.3197.
3197.
Okay. So that'll tell me how many moles are in that one little tablet that I ate. So 58.3197. So that is 0.00. So it's 1747 moles. Okay. So that's how many moles of magnesium hydroxide I have. What's the next step? What's my second step in figuring this out? So I know how many moles of hydroxide or magnesium hydroxide I have. What do I need to do next? Remember, I've got two things reacting with each other, so what do I need to do next?
Find the number of moles of HCl.
How am I going to do that, though?
Use a ratio.
How am I going to get the ratio?
Through an equation, like the balanced equation.
Bingo. That's what you need. You need the balanced chemical equation. Exactly. So this is my reaction. HCl plus magnesium hydroxide. And when you have a neutralization reaction, what are the two products? Anyone know what the products are of a acid-base neutralization reaction?
Water.
One's water, right?
And magnesium chloride.
Right, and the other one's the salt. The other one is a salt because you've got magnesium ions are going to be released and chloride ions are going to be released. And we know that that is a salt, right? We have a metal ion and we have a non-metal ion. That's a salt. And those are going to stay in solution. So that is going to be our other product, MgCl. What's the formula for magnesium chloride?
It's magnesium chloride 2
Which has a 2, the magnesium or the chlorine?
chlorine.
Chlorine, right. Chloride. There's 2 chloride ions because remember, magnesium is always 2+. It's in group 2 of the periodic table, so it's always, 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 always 2+. It's not a transition metal, so it's always the same. So now, is this a balanced equation?
No.
No, it isn't. I mean, we have our reactants and we have our products. Those are the actual reactants and products, but they're not balanced, right? So what do we need to do to balance it?
You need a 2 in front of HCl and a 2 in front of magnesium chloride.
Okay, so I put a 2 here because there's 2 chlorines on each side. If I put a 2 in front of the magnesium chloride, aren't I going to get?
I mean, 2 in front of H2O.
There you go. Right. Because really, we have, and we'll discuss this a little bit later. We have a strong acid, HCl. We have a strong base, magnesium hydroxide. And notice there are 2 hydroxide ions for every magnesium, but there is only 1 H+ for every HCl. In the overall, the net ionic reaction is H+ plus OH- makes water. So if this is a 2, this also has to be 2, and that also has to be 2 as well. So now we have a balanced reaction. So what is, now that we have a ratio, how do I figure out how many moles of HCl are going to be neutralized?
Would you multiply the amount of moles you have by 2?
Well, let's figure that out. So that is, we have 0.001747 moles of MgOH2. Now remember, you want to convert, basically all you're doing is another unit conversion. I'm converting moles of magnesium hydroxide to moles of HCl. So to do that, I put my MgOH2 on the bottom and I put my HCl on the top. So we see there's 2 here and a 1 is assumed there. So 2, 1. I get rid of my magnesium hydroxide and left with moles of HCl. So indeed, we wound up multiplying it by 2. But I always recommend you go through this procedure, though it seems like a pain. I mean, like, why am I bothering to do that? Because it's so easy to make that mistake of multiplying by 2 when you should have divided it, or divided by 2 when you should have multiplied. If you lay it out, you'll never make that mistake. Well, you'll rarely make that. You'll much more rarely make that mistake. So indeed, we multiply that by 2. So I have 0.001747. I multiply that by 2. And so I have 0.00349 moles of HCl. But I'm not done yet, right? Because I still have to figure out what the volume is. So that's how many moles of HCl. How am I going to determine what the volume is? Because that's basically the question. How do we get the volume of HCl?
You divide the number of moles by the molarity.
Never divide. Never divide. But remember, we always multiply, right? Always multiply. So what I'm going to do is multiply by the concentration. But remember, I want liters, and I want to get rid of moles. So that's, again, that's why I never divide, I always multiply with the units so I know what's going on. And so the concentration is 0.1 molar. And what does that mean? That means 0.1 moles for every 1 liter. So basically, yeah, you wind up multiplying this by 10. So my volume is 0.03494 liters. And so how many significant digits should I use to report this result?
2.
2.
2, right. There's 2 significant digits in the concentration, and there's 2 significant digits in the mass of magnesium hydroxide. So I'm limited to 2. So my final answer would be 0.035 liters. Or you could say 35 milliliters. Either one. All right, great job. And we were pretty close. All right, so I just want to talk a little bit about weak and strong acid. So have you guys talked about this in class already? It's kind of an important part of the lab today. You've talked about the difference between weak and strong acids, weak and strong bases. Yes, no? See? Is this new information?
No, I mean, it's in the lab manual, so.
Okay, I figured it was good to go over it because there is it's fairly profound difference between weak and strong acids. Anyone tell me what the basic difference is between a weak acid and a strong acid? Like there's one big difference. What is it?
Weak acids have a higher pKa.
Okay, that's right. But what does that mean? Like in more simple terms, what's the difference between a weak and a strong acid? I mean, you're right, but what's, like, put much more simply? If you wanted to tell this to someone who knew nothing about chemistry or pKa's or anything like that, and you wanted to tell them what the difference is between a weak and a strong acid, what would you tell them?
I probably would tell them that I didn't know either.
Okay. Anybody want to take a crack at it?
Is it that strong acids fully dissociate into their ions?
Oh man, yes, perfect. That's exactly the difference. A strong acid, when I dissolve a strong acid in water, it completely dissociates. And so I get all of it converts into H+ and whatever cation, whatever anion it's with. So like for instance, HCl is a classic, hydrochloric acid is like one of the classic strong acids. What does that mean? Well, it means that when I put HCl in water, I get the same concentration of H+ and Cl-. So if I have a 0.10 molar concentration of HCl, I know exactly how much H+ I have. It's the same amount because it dissociates into 1 mole of H+ and 1 mole of Cl-. So if my concentration of HCl is 0.10 molar, that's the concentration of my H+ as well, because it completely dissociates. Now with a weak acid, that's not true. With a weak acid, only a small amount of it dissociates, sometimes like less than 1% of it. And so you'll notice that with this reaction here, a strong acid dissociation, notice that the arrow just goes in one direction because that reaction is not in an equilibrium state. It does not go in both directions. H+ and Cl- do not reassociate back into HCl. this doesn't do it. So it's a one-way street. So that arrow points only in one direction. But notice when we have a weak acid, now the sort of the general way we represent a weak acid is say HA, which will dissociate into H plus and an anion A minus, and the A minus could be anything. In our situation today, it's acetate because we're dealing with acetic acid. But notice the difference. This arrow goes in both directions because acetic acid will dissociate into H plus, your acid, your proton, and acetate. It will also go back in the other direction. H plus and acetate ion will reassociate and form acetic acid. And in fact, with a weak acid, it's much more stable as the protonated form, as HA. Like I said, with most of them less than 1%, you get less than 1% dissociation. So you get very little H plus being produced. So in order to figure out what the concentration of H plus with a weak acid, now we need to know what the pKa is. We need to know what the dissociation constant is. And the dissociation constant is simply the concentration of H plus times the concentration of A minus divided by the concentration of HA. That is the Ka. That's the dissociation constant. That tells us every acid has a specific dissociation constant. The larger this is, obviously, the more H plus and A minus get produced. The smaller it is, the less H plus and A minus you get. And every acid, every weak acid has its own very specific Ka. And in fact, when we're doing titrations, we can identify what the weak acid, we can get the identity of a weak acid by figuring out what its Ka is from the titration. So anyone, what's the difference between Ka and pKa? What does pKa mean? What is that? What's P? What does that stand for? Like pH. What's the P for? What does it mean when I put a P in front of something? Lowercase p. Kind of tells you down at the bottom there. How do we determine pH? What does pH even mean? Anyone give me a definition of pH?
How acidic or basic in aqueous substances?
Mm-hmm. How do we calculate pH? What is it?
It's like on the scale from 0 to 14, every time you go up, you multiply it by 10.
Multiply what by 10?
The acidity. So if you go down, like it's 10 times more acidic than.
Right, it's on a log scale, right? pH is on a log scale. So what does pH actually stand for? I mean, it tells us how acidic or basic something is. But what does it actually stand for? What is it measuring?
Is it measuring the H plus?
In what way?
In
Measuring the what of H plus?
Mole.
The molarity, right, exactly. It's measuring the molarity of H plus. So if we can measure the concentration of H plus in molarity, for instance, the pH of 7 means that the concentration of H plus is 10 to the minus 7 molar. That's what it means. So putting a P in front of something means you're taking the minus log of a concentration. So the pKa is just minus log of the Ka, like it says here. It's just an easier way of representing a number, because if every time we had to say what the concentration, if we had to say what the pH of something was, and we said, well, you know, it's 10 to the minus 14th molar, like, or I could just say it's pH 14. That's much, much easier to do. So putting a P just means minus log. That's all it means. So it means that if the pH is high, that means the concentration of H plus is low. And the same thing with pKa. If the pKa is really big, that means that the Ka is very, very low, and it's an extremely weak acid. So the bigger the pKa, the weaker the acid is. All right. So here's some of the strong acids. We got 7 basic, really, really strong acids: hydrochloric acid, bromic acid, hydroiodic acid, nitric acid, sulfuric acid, hydrochlorate acid, and chloric acid. So you will see that strong acids, as we go up, are basically 100% ionized in water. As we go down, we get much less H plus produced when we dissolve them in water. And so these are really strong electrolytes and exist as completely as ions. So if I have a concentration, if I have a 1 molar concentration of HBr, for instance, I have 1 molar H plus, 1 molar Br minus. So they completely break down. So what does that mean? These are monoprotic strong acids. They all release 1 H plus. So the concentration of H plus, same as the concentration of the acid. Now let's look at strong bases. Strong bases are soluble hydroxides. So those are the alkali hydroxides, sodium hydroxide, calcium hydroxide. So they have to be soluble, for one thing. And some of the alkaline earth metal hydroxides, like calcium, strontium, and barium. So when you dissolve those in water, they completely dissociate in solution. So they give you OH minus, so hydroxide ion. So how much ever hydroxide we add, it gets completely converted to OH minus when it goes into solution. Now here's where something we probably haven't talked about yet: conjugate acids and bases. Is this a new thing for people? It's kind of important to explain the difference between strong acids and strong bases. Anyway, I'll just sort of explain it briefly. You let me know if you have a question about it. Now, a conjugate acid or a conjugate base means when I take an acid and it dissociates into H plus and the base that was there. If a base dissociates, it dissolves into a conjugate acid and OH minus. So for instance, here we have an acid, nitric acid. When I dissolve that into water, it produces H plus and nitrate or nitrite ion. So the nitrite ion is the conjugate base. So every acid has a conjugate base attached to it. So it's H plus a base, and bases are OH minus plus an acid. So when a base dissociates, you get OH minus and its conjugate acid. When an acid dissociates, you get H plus and the conjugate base, okay? So in this instance, water is actually a base. Water is actually a base and an acid because water will dissociate into H plus and OH minus. Right, we know that that's an equilibrium reaction. So water can both accept protons and it can donate protons. When it donates protons, it's an acid. When it accepts protons, it's a base. So in this instance, water is going to accept the proton from the strong acid and become a conjugate acid. So it was a base and it becomes a conjugate acid after taking in the proton. So acids have a conjugate base have a conjugate acid. Now, what does that mean? It means that it's the relative strengths of the conjugate acids and bases that tell you how strong the acid or base is going to be. I'll sort of just give you some examples. So here we have basically that same table where we have the acid and we have the conjugate base that goes with it. So strong acids completely dissociate, we know that. And why? Because their conjugate bases are very weak. Now, a weak base does not take a proton in. If it does take a proton in, it's a strong base. A strong base would be OH minus. When OH minus comes across a proton, it takes it in and makes water. When chloride ion comes across a proton, nothing happens, right? Because HCl is a strong acid. This reaction does not go backwards. It's a strong acid. So that reaction doesn't go backwards. So that means chloride ion is a very weak base. It does not accept protons. It's not a strong base. So if a strong acid will have a weak conjugate base. Now, on the other hand, weak acids have a very strong conjugate base. And so, for instance, let's look at H2 is an extremely weak acid. Why? Because its conjugate base is H minus, which is an extremely strong base. If you have hydride ion, it is going to react with H plus immediately and reform H2. So H2 is an extremely weak acid because anytime H minus is around, it's going to automatically reform H2. So it is not going to donate this proton. For H2 to be an acid, this proton would have to be donated to someone, and it's not going anywhere. If H minus is around, if hydride ion is around, it's automatically going to go right back to being H2. So it's an extremely weak acid. So weak acids only dissociate partially, usually around 1% or even less. So their conjugate bases are weak bases. Very, very weak acids have very, very strong conjugate bases. And so there's basically an inverse relationship between how strong an acid is and its conjugate base, or how strong a base is and its conjugate acid. So just making the point again, strong acids have weak conjugate bases, weak acids have strong conjugate bases, and the reason is weak conjugate bases give up protons easily. So they don't take back protons and push the reaction back in the other direction. They don't do that. And so any protons in solution remain in solution and being a strong acid. Now, if I have a weak acid, the conjugate base that forms, like for instance, what's the conjugate base we're going to be dealing with today with acetic acid? What's acetic acid's conjugate base? So hydrochloric acid, its conjugate base is chloride ion. Hydrobromic acid, its conjugate base is bromide ion. Acetic acid, its conjugate base is
Acetate.
acetate ion. Right, exactly, acetate ion. Because when it dissociates, we have an acetate ion and H+. Now, acetate ion is a fairly strong base because if I have acetate ion, it's going to pull H+ out of solution and turn it back into acetic acid. So that's why acetic acid is a relatively weak acid. All right, so let's get into what the experiment is. So you're going to be doing a titration today. And this is a titration curve down here at the bottom. And we're going to be dealing with this a lot in the report and in the third part of the experiment. So there's going to be the titration curve just tells you what the pH is as you add the titrant. Now, the titrant is what we're adding. And what we're examining is going to be the vinegar or the dilute acetic acid. The titrant is going to be the strong base. As we add strong base, the pH is going to change. And this gives you an idea of how the pH changes the more acid you add. Now, at the equivalence point, what happens at the equivalence point? So here's the equivalence point. What does that mean? What's the definition of the equivalence point?
Isn't it where the hydroxide ions and the hydrogen ions, there's the same amount of them?
Right. It means you have the same concentration of H+ and OH-. They're now equal to each other. And so you get a dramatic change in the pH then, because you go from having relatively similar concentrations to now having much more concentrations of OH- and having no H+ left over to react with it. And so once you start adding just pure OH-, the pH will shoot up. And so we should see a big increase in pH once you pass the equivalence point. Now, how do we know we're going to be beyond the equivalence point in a titration? What are we going to do to tell us where we are in the titration? How are we going to know that? Because we're not going to measure the pH, right? We don't have pH meters. So how are we going to know?
Color?
Why will it change color? Will it just change color by itself?
Like as we add the hydroxide?
Mm-hmm. What will happen as we add the hydroxide? The pH will increase, but why will it change color? Will it do so all by itself? You're right, something will change color, but it's not going to be the hydroxide and it's not going to be the acetic acid. What's going to change color?
Is it because of the pheno thingy? I can't pronounce it.
The phenolphthalein. Yeah, so what do we more generally refer to that as?
Catalyst?
Not really a catalyst because it doesn't catalyze a reaction. It doesn't speed up the reaction.
Is this called inductor?
Sorry, it's called what?
Induction or
No, it doesn't actually induce anything. I mean, it induces a color change, but in general, we just call it an indicator, right? Because it indicates that your reaction is over. So it indicates that it changes color at a particular pH. And so depending on the titration, we use different indicators. Phenolphthalein is clear when the pH is less than around 9. And then it turns pink when it becomes basic, when the pH is greater than 9. And you can see here, our equivalence point with the weak acid is going to be around pH 9 or so. And so it's perfect. That's when we want the color to change. If it was a different acid, or if we were titrating a weak base against a strong acid, we would want a different indicator, one that changed colors at like pH 5 or one that changed colors at pH 11. But in this instance, we want it at pH 9, and that's exactly where it changes color. So we need to remember, it's super important. We need to remember to add that, or we'll just keep adding hydroxide and nothing's going to happen. So that's at the equivalence point. So at the half equivalence point, which is around there, about half the volume it takes to get to the equivalence point, we call that the half equivalence or half neutralization point. Now, the reason why that's important, because at that point, the concentration of H plus and acetate ion will be the same. Why? Because at the half titration point, exactly half of the acetic acid will be converted to H plus and acetate minus. Exactly half. And at that point, the concentration of H plus and the concentration of acetate minus will be identical. And at that point, the pH is equal to the pKa. That is one of the ways we can figure out the identity of an acid, is by doing this titration, seeing what the pH is halfway along, because we know what the volume is at the equivalence point. We go exactly halfway, find out what the pH was. That is going to be the pKa of our acid. And so for the pKa of acetic acid is around, I think it's around 4.8 or something. And so the pH at the halfway should be about 4.8. Okay. So this is all background information that you should have in the write-up. I just want to explain it. So here's a strong base weak acid titration. This is the one we're going to be doing today. And this is a titration between a strong base and a strong acid. Why do they look so different? What looks different about them? Can you name some things that look different about them?
The equivalence point is neutral. It's at 7.
Right, with a strong base and a strong acid, it changed that once you have H plus and OH minus equal each other, that's the pH 7. Whereas with the strong base and a weak acid, our pH is around 8.5 or 9. So that's one difference. What's another difference? What's the pH at the beginning for both? Compare the pH at the very beginning of our titration for the weak acid and the strong acid. What do you notice about it?
It's not at 0 for the weak acid.
Yeah, for the strong acid, the pH is much lower, right? meaning that for the same concentration of acid, I get a lot higher concentration of H plus when I have a strong acid. And that makes sense, right? Because it completely dissociates. I put the same concentration of a weak acid, I got much lower concentration of H plus, and my pH, therefore, is going to be a lot higher. It's going to be, I'm going to have I'm going to have more H plus than OH minus in there, but not nearly as much. So my pH is much, much higher as I go. Another difference is the shape is a lot different. Notice that this shape here is a lot different than the shape here. Here, with the strong acid, strong base, I get a very sudden increase in pH. And with a weak acid, I get it's much more gradual. And that's because the weak acid is constantly pulling H plus out of the solution. Basically, what I'm doing, strong base, weak acid, what's happening is that the OH I'm adding is battling with the acetate ion. They're both pulling protons out of the solution. It just happens that hydroxide is a much stronger base than acetate, and so it will basically pull the proton away from it. But they're both sort of battling for it, and so the pH changes much more slowly and much more gradually. When I have a strong base and a strong acid, all of the H plus and all the OH minus are in solution already. And so when they equal each other, I get this instant change. This is called buffering. And for those of you doing biochemistry or else later on, you'll be doing a lot of making buffers. Buffers are extremely important. Like your blood is buffered by the presence of a weak acid, carbonic acid, which you get by breathing in CO2 and it interacts with water. Carbonic acid is a very weak acid. When it dissociates, you get a weak base called bicarbonate. And it varies, it keeps the pH of your blood around pH 7.4, 7.5. So what a buffer does is it keeps the pH relatively constant. You can add acid to it, you can add base to it, and the pH really won't change very much because you have a weak acid and a weak base, both present. One will take in the H plus, the other will take in the OH minus. All right, so let's just go over what it is you're going to be filling out. So this is the first part of the experiment where you'll be using the vinegar that comes with the kit. If you don't have the vinegar that comes with the kit, just regular old white vinegar will work. So what we're going to do is we're going to measure the mass. We're going to take about, I think it's 10 mils or 5 mils. I can't remember. Well, we'll look at the before we start. We'll review the actual procedure. And so we measure the mass of the vinegar because we can measure mass a lot more accurately than we can measure volume. So we'll measure the mass of the vinegar in our 25 mil little beaker. It's a flask. Then we'll figure out what the volume is. We'll put sodium hydroxide of a known concentration in a syringe, and we'll just add it by, there you go. We'll add it by half mils at a time until with swirling, until we start, basically what you'll do is like you'll keep adding. You'll notice it'll change pink. You get a little bit of pink color. And then when you swirl it, it'll go away. Because basically what that happens is if it's not mixed completely, in some small part of the solution, there'll be more OH minus from your hydroxide. And the phenolphthalein in that little part will turn pink. And then the minute you swirl it around, it will mix and the pH will go back down again, or go back up, down. So that'll let you know that you're getting close to the titration point. So when when it takes longer and longer shakes to get rid of the pink color, we'll start just going drop by drop. And then we'll measure the volume of the solution we use. Since you know the volume and you know the concentration, we'll be able to figure out the number of moles of acetic acid in that sample. We figure out what the mass of the acetic acid sample is. You figure out what the mass of the water in there is, and you get a calculated percent mass of acetic acid. You should get around 5%. That is the concentration. That's roughly the concentration for most commercial white vinegars. So you should get around 5%. Now, so that's fairly straightforward. So you'd be doing that for the known sample. You'll be doing that a triplicate for the known sample, and then you do it for an unknown sample. So you should have some like rice vinegar or any other kind of vinegar you have in the house, like a white wine vinegar. I noticed that we have like a red wine vinegar, but that's not really going to work because it's already red. So we're not going to be able to tell the color change most likely. But if you have white wine vinegar or rice vinegar, that will also work as an unknown, okay? And then lastly, the data table here, the third one, is basically is an additional exercise where it gives you data from a vinegar titration with a known amount of acetic acids. Here's our known amount of acetic acid, 21.05 mils of acetic acid. The concentration of the sodium hydroxide is 1/10 molar. And it gives you all this information, like what was the pH at the beginning of the titration? And it's using a burette. Anyone tell me what a burette is? What's a burette? Do we know what it is? Have you seen a burette or seen a picture of one? No one's seen one? Or have you talked about it in class, seen a picture of one? Yeah, John, it is. It's like a long pipette, exactly. So think of a burette sort of like this, but instead of a syringe pushing down, we just have a little stopcock on the bottom. We take this out, and we just freely when we open it up, we open up the valve, it freely lets water come down. And they're normally much larger, normally hold about 50 to 100 mils. And they're very, very tall so that you can read the volume very, very accurately. So you take the initial volume. So if the initial volume is 1.61 mils, and you turn the stopcock and you're letting liquid come out, at the end of the titration is 19 mils. And so the total amount of sodium hydroxide you used was 19 minus 1.61 mils. So that tells you what the total volume was, okay? So what you need to do with this one is figure out what was the volume of sodium hydroxide dispensed. That one's pretty straightforward. Calculate the concentration of the acetic acid in the sample. That one's also pretty straightforward because when you figure out what the moles of NaOH, you're going to know what the moles of acid were. Figure out what the concentration is. And then it also gives you what it was at the midpoint. So remember I said that's like the half titration mark. And if you remember at the half titration mark, A minus and the concentration of acetate and H plus are the same. So you use this equation, that's the Henderson-Hasselbalch equation. That's also in the write-up. You can figure out what the pKa is. You go backwards. What was the pH at midway? What was the concentration of A minus an HA plus, and you can figure out what the pKa is. Okay? So I'm sure there'll be some questions about that after. But let's like take any questions before we get started with the experiment? I sort of prattled on for quite a while there.
Yeah, for activities 1 and 2, are we doing it 3 times? Because it says sample 1, 2, and 3.
Yeah, we're doing them in triplicate. Mm-hmm.
Okay. So we do it like one after the other?
Yeah.
Okay.
Yeah, these don't take very long to do. So I mean, you'll see it takes like maybe 5 minutes per run. So it won't take very long to do. And then so the point of doing that is like, there's going to be some error. There's always error in doing these. And so if you do them in triplicate, you can see if you have an outlier, for instance, like if you get two runs that look almost identical to each other and one that's like really different, well, you must have made a big mistake with that one. You toss it and you take the average of the other 2. Or if you have 3 that look relatively similar, then you just take the average of those 3. Because you're going to calculate the percent acetic acid 3 times. And so let's say you get 4.5, 5.2, and 6%. You take the average of those, and it'll probably be pretty close to 5, which is, I think, what we should be getting. Because that's commercial vinegar anyway. You can get acetic acid. I mean, the acetic acid I used to buy was like extremely concentrated and very dangerous, actually. It was 14 molar. So it was like, yeah, it was pretty concentrated stuff. But for vinegar, I think it's around 1, it's a little over 1 molar, something like that. So we'll find that out today. Any other questions?
And then is there a reason that those are orange, the boxes?
I think it's because there's no midpoint pH or burette readings there, so you can't figure out you can't calculate pKa from those because you don't know what the pH was at the midway point, and you need to know that.
Oh.
So you don't have to figure those out, but for sample 2 and 3, you do.
Okay.
Yeah. And so your calculated pKa should be somewhere around, it's between 4 and 5. Like the actual pKa is between 4 and 5. Any other questions? All right, so I'll give everybody about 5 minutes to, get their stuff together, get their goggles on, get their cameras on, and then we'll do the experiments, okay? All right, let me. Okay, so I put up the procedure here so we can all have it. One thing I would probably do, it says to weigh the 10 mil graduated cylinder. What I would do is actually weigh the, we're going to be pouring into the flask. I would weigh the flask. So actually what I would recommend is we put the flask on the we determine the mass of the flask, and then we'll put our 5 mils of vinegar in the flask. And because if we don't transfer all of the volume of the vinegar from our graduated cylinder here, it's not going to show up in our flask. I want to know exactly how much we transferred to the flask. So I think that's a bad point on their part. So Roger's going to weigh out. He's going to measure 5 mils. And you don't have to have exactly 5 mils, Roger, because what we're going to do is we're going to determine exactly how much gets put in here. So around 5. It doesn't have to be, like, approximately 5. If it's 6, that's fine.
Five and a half-ish.
Okay, there you go. Now we want to tare this so it's 0. Okay, there you go. and just empty the whole thing in there. See, because now we can measure precisely the mass. So we have like 5.31 grams of vinegar,
That's vinegar.
precisely. Yeah, you can smell that, right?
Yeah.
Yeah, so we're going to write that down. So we have 5.31 grams of vinegar. Now, using the density of the vinegar, we'll be able to convert that to a very precise volume. So we take that off. And we're going to add 2 drops of the indicator. This is the indicator here. Now that will change color when the pH goes up. Yeah, if you get 3 drops, that's not a problem. There you go. Then swirl it around, get it all mixed up. There you go. So because this is acidic, is the pH going to be low or high? You remember?
Pretty.
Other way around.
Okay,
Yeah, pretty low.
yeah.
And when the pH goes up, it'll change color. So we're going to titrate. This is what we're going to be titrating it with. This is kind of dangerous stuff. So I'm going to put it in the. So you want to put about 10 mils of the sodium hydroxide. Well, I don't plan on splashing it on myself.
Yeah. But
Into a cup. All right, so what you're going to do, Raj, is take the syringe and pull it up to 10. There you go. If you got an air bubble in it, that's fine.
Yeah.
Just keep pulling it up. Turn it upside down. We just sort of tap on it, get the air bubble out. Doesn't appear to want to go. There it goes. And then we just squirt it out. Okay. There's a little one.
Yeah.
So we just get it down till it's right at 10. See how it's right at 10 there?
Yep.
All right, we're ready to go. Let me just wipe that off. Just a little bit on me. All right, so what we want to do is put about 1/2 ml at a time in there and swirl. So what's important, everyone, notice that we have our, I don't know if you can
Whoa.
see. Yeah, see that? It turns pink pretty rapidly, right? And then when you swirl it,
It's gone.
it's gone, right?
It's a very vivid pink color.
Yeah, it's super vivid, right? Swirl it, swirl it, swirl it, and it goes.
Gone.
Yep.
Well, there's a tiny bit in it.
Yeah, so about 1/2 ml at a time. Yeah, it's pretty color, isn't it?
Yeah.
So it's important that you have like a white background underneath your flask here, because
Otherwise, you can't really.
it's tricky. It'll be tricky to see. It's pretty easy to see the pink color appear, but what you're going to be looking for is it at the titration point. You want it to be just barely pink. If it's super pink, you've gone too far. So you keep mixing it. See right here, there's like a little bit of pink there. I don't know. Here we go. Oh, it's gone. But at the titration point, if you can't, when you stir it, when you mix it up again, if it's still like super bright pink, you've gone too far. You want it to just be very pale, very pale color of pink that doesn't change after swirling. That's perfect, the titration. So right now you're fine. So we'll just keep adding 1/2 ml at a time. And then once it gets to like really, really close, we'll just add a drop at a time, okay? Yep, swirl it. There it goes. Cool, right?
Yeah.
Yeah, don't be in a hurry to get to the end point, because if you're in a hurry, you're going to go past it, and then you just have to repeat it again anyway. Yeah, if you have a little bit of drop, yeah, just let it, there you go. Give it a swirl. Ooh, must be get, oh, I think we went a little too far. Let me see.
Oops.
That's all right. We're going to do it again anyway. All right, so let's see. So what's the volume on your syringe now? What does it say?
It's like about 6, no, 5.5.
5.5? Okay.
Yeah.
So it's at 5.5. We started at 10. So what, how much did we put in here?
4.5.
4.5, that's right. So we put in 4.5 mils. So that tells us, so we went a little bit over. You see what the color is. This is way too bright.
Yeah, it went from.
But it's not a complete waste of time, because we know that the titration point is going to be around 4.5. So what we'll do next time is we'll like rapidly go to 4 and then go drop by drop, and we should get it a little bit better. So let's just do it again. So that was our first one. So our first one was 4.5 mils.
Yep.
And we know that one's probably a little bit much. So I'm just going
A
to
bit.
dump this, and we'll do it over. Give it a rinse. Yeah, pretty cool, right?
Yeah. Although it went over really fast.
Well, that's just it. The pH, when you get close to the titration point, the pH changes really fast. So it changes a little bit and a little bit and a little bit, and then all of a sudden, boom, it changes very quickly. So let's do that again with another 5 mils of vinegar. So the second and third one you do, if you have a little bit of water in your flask, that's fine. Because remember, we're not worried about the concentration of the
Again, 5.5.
vinegar. We want to know the number of moles. So that's what's going to, all right, go ahead.
Can this go down the sink?
Yep, that's fine.
Okay.
And then if you go too far, should you still record those results, or do they not count?
I would just do it again. I mean, you know, you have plenty of material to do it multiple times. Yeah, we're gonna do it a couple more times. Okay, so 5.38 this time. All right,
Yep.
cool. All right, so let's go back up to 10 again.
Yeah. Because of the angled stopper.
Oh,
Bit
what if we forgot something? What have we forgotten? Before we start, what do we need to? Forgot the indicator.
Oh yeah, indicator.
Yeah.
That would have been.
Yeah, nothing would have changed. We would have known very, very quickly.
Yeah. 1, 2.
Yeah, there you go. All right. Yeah, so this time when we get down to around 6 mils, we'll slow way down.
So just.
There you go. So has anyone finished the titration? Did you get around between 4 and 5 mils?
Yeah, I got 4.4.
Oh man, so we were really close, Raj.
Yeah.
I got like 4.1.
There you go. So is everyone using the vinegar in the kit, or are they using their own?
The kit.
Okay.
Okay. we're
Of course,
getting-
remember, it's the amount of sodium hydroxide you add is dependent on the amount of vinegar you have. So like maybe not everyone used exactly the same amount because we used
Okay, so we should probably slow down.
we used 5.38 grams, 5.31 grams. So if you use less or more, obviously it's going to be a little different. So we're really close, are we, Ron?
Pretty, yeah.
Okay. So it looks like we have a drop up there. So yeah, tap that. And see it's there it goes.
White.
Yep. Yep. So we still got a ways to go. We'll sneak up on it this time. Okay. Or you can just, yeah, there you go. Yeah, this works better than I thought. So remember, your volume should have 3 digits. So we're going to remember the first 2 are going to be based on the lines on the syringe, and the third one is going to be your estimation of the volume between those lines.
We should be getting pretty close.
Yeah, it looks pretty close. There you go. Yeah, we're just going to want it just a faint pink color at the end. Ooh, man, you're close. Yeah.
That pink, I can't really tell.
I don't think so. I think that looks pretty clear to me. But yeah, you're really quick, probably like maybe 2 or 3 drops away. Yeah, I had a professor in college who would yell at us for saying your drops are too big. You should be adding quarter drops. He was kind of crazy. Yeah, exactly.
Like that?
Yeah, I don't know how he expected us to do that, but that's why I got a B in that class. Oh man, yeah, maybe 2 more. I think you got it. See how it's taking longer and longer for the pink color to go away?
Yep.
Yeah, that means you're super, super close. Yeah. Keep going.
This is gonna take a while.
How long?
A while.
Yeah, I mean, you're less than 5 drops away, so.
And more pink colors.
Nope, still left. Yeah, it should be just the palest color pink possible.
It's too dark.
Let me see. That's pretty dark. Yeah, you want it to be really, really pale. Like you can barely, that's why the white paper is so important. You want to be able to just barely see pink at all. But I mean, the thing is, you're probably like 1 drop over. So it's probably fine.
Kind of pink.
But the perfect titration is just barely pink. Like you can barely see it, but it doesn't go away when you stir it. Oh man, yeah. I think 1 or 2 more, and you got it.
Yeah, I think like 1 more is probably.
Yeah, no, see as it turned pink on the way down.
Yeah.
All right. Yeah, I think that was your half drop. So let's try 1 more. Okay. All right, let's see. Does that look pink to you?
I can't tell, really.
All right, one more. Well, the thing also, if you're not sure if you can see the pink color or not, write down the volume as where you think you might have seen it. Add another drop. If it turns bright pink after that, you were right to have written down the volume before. So write down the volume, add another drop, and if it turns bright pink color, then you were right the first time.
Okay, that's kind
And
of.
take that volume.
That's kind of pink.
Maybe. All right, what volume do you have?
Almost exactly 6.5. But
Yep,
a bit over.
bit over. Okay, so one more. So let's say 6.55.
Yeah.
So if this drop doesn't turn back, I think that's it.
Yeah.
So what's, so 6 point, oh, actually 5.1,
Oh, really?
5.2.
And it still went away.
Oh, man.
Okay, this is just getting redonkulous.
All right. Is that it?
Yep.
There it goes. Okay.
Okay, so a tiny.
5.15. So that is, so we subtract that from 10, and that's 4.85 mils. Okay, excellent.
That took a while.
It did. All right, yeah, so it seems the sweet spot is like going to be between 4 and 5, depending on how much vinegar you do. So we're going to do one more, and then we're going to average our results.
Really vivid.
Yeah, that is vivid. Yeah, so it went from 0 to 100 pretty quick, right?
Yep. Kind of like an avocado.
Exactly like an avocado. Unripe, 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 unripe. Oh, too late.
No, you didn't. You didn't have like a millisecond of now I am the best.
Best
food
best
that
thing ever.
Just ever.
All right.
And now it's.
And
all
now
around.
it's mushed.
Yes.
All right, so we'll measure out 5.
Okay. Whoa.
Wait, what do you do if you went too far?
Well, if you went too far, you went too far. Just do another one.
All right.
I mean, if it's like just like red rather than pink, yeah, that's too far. If it's pink, then yeah,
Okay.
you're going to be. It's pretty close.
Almost exactly 5. That was...
Man, this smells bad.
Yes, yes, it does.
All right, so we're
Okay,
at
so I got 485.
485. So it'll be a little bit less this time.
Yep. Then
438.
indicator.
Oh, sorry, what was it?
485.
484. Okay.
So
4.5,
2 drops
4.5.
of this.
Yep.
2.
Since we added less vinegar this time, we're going to
Yeah.
need less of this solution as well. So you'll probably go to like 3.5 and then slow down. There you go.
Go to there?
No, I mean,
Okay, yeah.
go to
Yeah, I was
go to the 7.5.
Okay, that
Yeah.
makes much more sense.
Uh-huh.
Still in half.
No, you can just go right there because
Okay.
we know basically what it's going to be.
That's very pink.
Mm-hmm. But it will,
And yet,
yeah, it'll go away. Yes, your second and third titrations are going a lot faster because you can zip right up to close to the titration point and then slowly go. So even if you go over your first one, you're going to know basically where the titration point is. And so you can go there fairly quickly. You don't have to go half by half, half mil by half mil, because you know where the titration point should be approximately. So we know ours is going to be around 4 mils. So we sort of just went right to it. And now we're going to start going drop by drop. Oop. Over.
already.
Yep. So what do we have? 6 or 5.8. Okay.
Yeah.
So 4.2. Okay. You want to do one more or?
Sure.
Okay.
Might as well, since 2 of them went over. And the third one.
Yeah, one of them is really good.
Yeah.
And it is often, I mean, basically, we're not using materials made for this. We shouldn't be using a syringe. We should be using a burette.
Yeah.
But we don't have a burette. So we're making.
Making do.
Exactly. All right, so be our last one.
I think I got it pretty close this time.
There you go. There you go. So it's a 507, okay?
Yeah.
You don't cross your sevens? Like a scientist does?
So we can, since it was around,
Yeah, so we want to,
like 5.
yeah, we want to go to like 6 and then go very slowly from there. Oh, I think you forgot something.
Oh yeah, we forgot.
Mm-hmm. Whoa.
Whoa, that looks cool. And it stirred up itself. Okay, so we're at 6.
Mm-hmm.
So now we should go.
Oh, you're close. All right, let's see what the volume is here, just in case the next one. So that's pretty much 6.1.
Yeah.
All right, there you go.
$6.15.
It should be less.
Oh,
It's that first mark. So it's right at 6, actually.
Yeah.
Yeah. Yeah, you might as well put that drop in there because it's going to show up. Yeah, so I think a drop will do it.
Yeah. So this is
5.9.
maybe 5.85.
Okay.
So is the third sample the only one that we use like a different vinegar?
So you should do, I think you do 3 of each one. That was my understanding.
Um,
3 for the vinegar sample that was included in the kit, and then 3 for an unknown, like one you have in the kitchen.
I think 5.8 or 5.75,
Okay.
somewhere in between.
That might be it.
Nope.
Oh, man. So close. Nope, not quite.
I think this one's probably good. 5.7.
Okay. Right on 5.7.
I don't know.
Man, it's hard to read, isn't it? Yeah,
Yeah.
It's close enough.
Especially with the
Mm-hmm.
angle.
Bingo.
Yep.
Right, 5.7. So that's 4.30. Okay,
And then there's-
excellent.
Okay, I think we got that.
Thank you.
Pretty. That's a very, very reddish pink, I guess.
Excellent job.
Okay.
Stuff up. I'm going to move the computer back.
Okay.
Excellent work. You want to rinse this off in the sink?
There you go.
Oh, this one too?
Yep.
Thank you. All right, it's going to move back to the table.
Whoa.
Yeah, you could add a whole bunch of water to that. It's not going to change the pH much.
Yeah. Well.
Yeah, it gets more dilute, so yeah.
Yeah.
The pH scale is logarithmic, meaning each number is 10 times bigger than the last one. So
Yeah.
pH 5 is 10 times more acid than pH 6. So you would have to dilute that 10 times just to change the pH by 1 unit.
Wow. So where are we going?
I'll just put it back there. Oh,
Okay.
I can unplug that.
And
Thank you,
then
Roger.
this goes in the trash.
You're an excellent chemist as usual.
Oh, these hurt my eyes.
Your head or your eyes?
Yeah, well, just the area around my eyes, and then by default, my eyes too. By extension, my eyes.
right, so how's everyone doing? If they got at least 2 done already?
Yeah, I did. I keep like doing like it's clear, and then I add one more drop, and then it turns like red. It's
Yeah,
really-
that's what's going to happen. You saw from the titration curve that at the inflection point, at the titration point, the pH changes radically. So it goes from like a pH of around 4 or 5 to a pH of 10. So it changes 5 pH units in less than a drop. So that's why titrations are still used all the time in like industry and everything, but we don't have people doing them. We have robots doing them, and they can add microliters or even nanoliters of titrant at a time and monitor the color of the solution much more accurately than we can. So they get extremely accurate profiles so they can calculate the pKa down to like, with 4 significant digits. We can't quite do that with our fumbling eyes and fingers. But we should be able to get pretty close, I think, to 5%. So I was just going to go over some of the, actually, I'll just be available for taking questions, and then we can start looking at the calculations. So is everybody doing it today, or the rest of you who haven't got your cameras on? Are you not doing the experiment, or just don't have your cameras on?
I'm doing the experiment, except I just got back from vacation and my room is a complete mess. So yeah.
Fair enough. Yeah, I just want to make sure. You have your goggles on and everything.
Yeah.
Okay. Yeah, because I'm not too worried about vinegar. I mean, if you get vinegar in your eye, it's not that big a deal. But sodium hydroxide is bad. Sodium hydroxide will dissolves things.
I got
organic things like skin and eye lenses and stuff. Kenneth, you had a question?
I got a drop of sodium hydroxide on my laptop. There's like a stain. How do I get rid of it?
Oh, just with a napkin. Just you want to get that. You want to get rid of that as quickly as you can.
It's not working.
What do you mean?
It's not coming off.
Is it in the keyboard or?
No, it's next to the trackpad.
And you can't get it up with like a paper towel?
No.
Try just like a damp paper towel then.
Do different types of vinegar have the same density?
Well, no. That's a really good question. The density that's given is for just sort of regular white vinegar. If you've got rice vinegar or something, it should be probably pretty close. It won't be exact, but it should be fairly close.
Is it something we should look up, or can we just use what we
Hey,
get?
yeah, exactly. Yeah, I mean, I doubt the density is going to be on the label. I mean, it might, but yeah, if you could look it up, that's perfect.
Okay.
Which other vinegar are you going to try?
Rice vinegar.
Oh, okay. Yeah, I thought we had rice vinegar, but it turns out it was rice wine. Oops. and like I said, the red wine vinegar we have, that's not going to work too well.
Yeah, I was gonna use apple cider vinegar, but it looked really dark.
Yeah, I mean, you can dilute it. If you can dilute it and then titrate. You can do that.
Oh, okay, thanks.
Because so if you take like 5 mils of the cider vinegar and add 45 mils of water, You can still do the titration. I guess if you're using the 25, you can add like 10 mils of water or so. It won't affect the moles of acid in there.
All right, so the stain is not coming off. Do you have any other ideas?
Oh, it's a stain. Oh, okay. Just use vinegar. Because I mean, it's a base, right? So you want to neutralize it. Use a damp cloth with some vinegar on it. Now, if that doesn't get it off, then I think it's just going to be stained. It's not the screen, is it?
No, it's next to the trackpad.
Hmm. Yeah, you want to. I misunderstood. I thought you couldn't get the liquid off. Yeah, so use a damp vinegar and see if that takes the color away. It looks like it's bleached, basically.
It's sort of white.
Yeah. Yeah, basically you've oxidized the plastic, or whatever's dye is in the plastic. You've oxidized it with the hydroxide ion. So you may be able to reverse it with the acid, but maybe it might be too late. Oh, whatever vinegar, John. Yeah, whatever vinegar you have. Or lemon juice. I mean, anything acidic. Anything that's like sort of mildly acidic.
I used apple cider vinegar, but is it supposed to turn this red or no?
So that's after your titration?
Yeah.
Yeah, that looks fine.
Okay.
So I mean, how dark was it before you started adding the hydroxide? Oh, yeah, perfect. Yeah, you sort of like, the way we've been doing it, sort of mix, 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 mix. And when the color disappears, if it takes a really long time for the color to disappear, make a note of what that volume is. And then if your next drop turns it bright pink, then that last volume was the actual inflection point. Because like I said, it should be extremely pale, and sometimes so pale it's kind of hard to see, especially if your vinegar is already colored. It's going to be trickier to pick up that really dilute pink color. All right, so I was just going to go through how to do these calculations. And I'm taking some of the data that Roger came up with. And so one of his titrations was we started out with 4.48 grams of vinegar. So we convert that to milliliters by using the density. And I believe the density is 0.005 grams per mil. Is that correct? I think that's right. Is that the density they give you?
Yeah.
Okay. So then we convert that to the actual volume. It's going to be pretty close, obviously. So 4.816 mils. And don't worry about rounding. I'll do that at the end. So that is equivalent to, when you divide that by 1,000, 0.004816 liters, right? So we'll go 1, 2, 3 to go from mils to liters. So with that amount of vinegar, we used 4.2 mils of the sodium hydroxide, which is 1 mole for every liter, which is also equal to 1 mole for every 1,000 milliliters. That way we get the canceled milliliters, and we're left with 0.0042 moles of hydroxide ion. Now our balanced equation is 1 mole of acetic acid plus 1 mole of sodium hydroxide gives you 1 mole of sodium acetate. So this is the acetate ion here, CH3COO and Na+. So we get, that's the salt that's now in solution, and we get water. And it's a 1-to-1 ratio. So for every 1 mole of sodium hydroxide, that neutralizes 1 mole of acetic acid. So if I have 0.0242 moles of hydroxide, that's how many moles of acetic acid I have. So that's how many moles of acetic acid I have. That's the volume of acetic acid I have. And moles over liters is molarity. So my molarity is 0.872 molar. But we want to know what the mass percent is, because that's what the concentration is generally given, is in mass percent. So what does mass percent mean? It means mass of acetic acid over mass of solution. So, and then multiplied by 100. So if we have 0.872 molar, what that gives us is 0.872 moles of acetic acid over 1 liter of solution. So we convert both of those to masses. What's the mass of 0.872 moles of acetic acid? How do I figure that out? So I need the mass of the numerator, and I need the mass of the denominator. How am I going to get the mass of the numerator? How do I determine the mass of 0.872 moles of acetic acid?
Multiply it by the conversion factor of the molar mass of acetic acid.
There you go. Yeah. So it's 0.872 moles times 1 mole of acetic acid on the bottom. and the molar mass of acetic acid, which is 60.052 grams. So that's how much a mole of acetic acid. That's the molar mass of acetic acid. So I multiply those together times 60.052. That gives me 52.37 grams. So that's my numerator, 52.37 grams. That's how much. And so I'm doing it for a liter because it just makes the calculation easier. I could do it for like 10 mils or 5 mils or whatever my volume was. This just makes it a lot easier because I figured out that the concentration is 0.872 molar. Well, what does that mean? That's how many moles in the liter. So my numerator is 52.37 grams. What's my denominator? What's 1 liter? What's going to be the mass of 1 liter of vinegar? How do I determine that? I mean, I can approximate it and say that I could use the mass of water and get it approximately, but I don't have to do that. I can calculate it more accurately. How can I calculate it more accurately? So how do I go from volume to mass? What's the relationship between volume and mass?
Density.
Mm-hmm. Precisely. So what's my density for vinegar? That's given, right?
1.005 grams per milliliter.
Right. So 1.005 grams per milliliter. Well, 1 liter is 1,000 milliliters. So I multiply 1,000 by 1.005 and I get 1,005. So in 1 liter of vinegar, I have a total mass of 1,005 grams. The mass of acetic acid in it is 52.37 grams. So my mass percent of acetic acid is 52.37 divided by 1,005 times 100. I'm going to get pretty close, actually. I'm impressed. So 52.37 divided by 1,005 times 100 is 5.2%. So I said we should get a percentage of around 5%. Well, there you go, 5.2. So man, I'm gonna have to tell Roger he's a better chemist than his old man, but I think he knew that already. Yeah, so that's what they're looking for. They're looking for mass percent. So you're going to do this. So you're going to have 3 different values and just and give the average. So any questions about how to get the percent? You want us to go over this one more time?
Could we go over number 3 from the pre-lab questions?
Oh, of course. Yeah. So just remind me, what was the question?
Says, for each of the above points, identify the ions and acids present and sort based on their relative concentration in the solution. Okay.
So it gives a, let me see if I can pull that one up. Because there's a lot in that one. See if I can find it. All right. Okay. Right. So it's basically asking about the titration we're doing right now. So I can just go back to the slides and pull that out. All right. All right, so it's asking about the titration on the left, which is the titration we're doing with a weak acid, and the particular weak acid is acetic acid, and the strong base is the hydroxide, just like we're doing now. So it asks you to find different points on the titration curve. So what are the points it's asking for? It's asking for the 4 different points, right?
The start of titration.
So right here. Mm-hmm.
The midpoint.
So about there, right?
Yeah. And then the equivalence point.
Okay, here. And then afterwards, right?
Endpoint, yeah.
Okay. And there. So 4 different points in the titration. And so these are the different species that are going to be there. So the different species that are present at any time are going to be acetic acid, acetate ion, protons, sodium, and hydroxide ions. So these are the 4 ions that are going to be there: acetate ion, sodium ion, protons, and hydroxide. And then the acid will be acetic acid. So those are the 5 things we're going to be looking at in terms of who's present and in what concentrations, okay? Those are the 5 things. So 1, 2, 3, 4, and 5. So at point A here, so this is point A. What's present at point A? Of all the things we've got here, what's going to be present?
Acetic acid.
Right, so acetic acid is going to be there. What else?
H plus.
So we're going to have acetic acid. We're going to have H plus. What else are we going to have?
And acetic ion.
Yeah, acetate ion. So this. Now at this point, we're not going to have any sodium because we haven't added any yet. And we're going to have very little hydroxide. There's always a little bit of hydroxide in water, just even in pure water. There's a tiny, tiny amount of hydroxide, but barely any. So we can basically ignore it. So of these three things, which one's going to be in the highest concentration?
Acetic acid.
Yep, exactly. Because it's a weak acid. So like we said, with a weak acid, only about 1% of it, or less than 1% of it, ionizes. So the vast majority, like 99% of the acetic acid present, is going to be in that conformation with the proton attached. And then the H plus and acetate ion are going to be there in relatively the same low concentrations. So we would go 1, 2, 3, and 2 and 3 being basically the same. So that would be for A. Now, what about B? What's going to be present at B?
All of them?
Yeah, all of them. Exactly. What do we know about the concentration of H plus and acetate ion halfway through the titration?
That means half of the acids and bases are neutralized.
Right. It means you've neutralized exactly half of the acid. You've neutralized half the acid. So what does that tell us about the concentration of the acetate ion, the acetic acid, and the H plus?
That they're equal.
They're all the same. Exactly. They're all the same. Because exactly 50% of the acetic acid, let me start over. So if my reaction is this, CH3OOH goes to acetate plus H plus, they're now going to be the same. So the concentration of this and the concentration of this are going to be identical. And the concentration of H plus is going to be the same as whatever the concentration of OH minus is. And that's going to be turned into water. So they're all the same. So basically, if halfway through, these are all the same, and my concentration of sodium and hydroxide is half that.
So, wait, can you repeat that?
Actually, the hydroxide, hydroxide is the same, is half the concentration of everybody.
And then the sodium is?
It's the same. Because remember, the concentration of the sodium and the hydroxide is always going to be the same because that completely dissociates.
So the concentration of the sodium hydroxide is half the concentration of the acetic acid?
Right.
Okay.
Yeah, because we're halfway to the equivalence point. At the equivalence point, the concentration of the acid and the base are identical. So that takes us to C. So at C, what's going to be my concentration of acetic acid at C at the equivalence point?
It's going to equal the concentration of the sodium hydroxide, right?
Actually, no. The concentration of the acetate will equal the concentration of sodium and hydroxide ion. Because remember, at the equivalence point, all of the acetic acid has been turned into acetate and H plus. So basically, the concentration of acetic acid at the equivalence point is 0 because it's gone. It's all been converted to acetate ion. So there's none left. So at A, like 99% of the acetic acid was in the acetic acid form. At B, 50% of it is in the acetic acid form. And at C, none of it is in the acetic acid form. It's all been converted to acetate. So at that point, acetate equals the concentration of sodium ion. And basically, the concentration of H plus is also pretty much at 0 as well, because that's all been converted to water by hydroxide ion. So my concentration of hydroxide ion and sodium, and hydroxide ion and protons are around the same and very small. That's why the pH is around 7 or a little bit more than 7 at the pH, because they're almost the same. At pH 7, the concentration of the protons and the hydroxide ions are exactly the same. That gives you pH 7 when they're identical. And then in this instance, they're almost the same. And then the minute we add any more hydroxide ions, all the protons are gone and we just have hydroxide ions left over. So at D, again, we have no acetic acid. It's all been converted to acetate. And that acetate is not changing concentration. So now our concentration of sodium ion is now higher than acetate ion, because we have a little bit more sodium hydroxide than we do acetic acid. But there's no more acetic acid left because all those protons have been removed by hydroxide. So the most abundant ion now would be sodium, followed by acetate, followed by hydroxide.
Okay, so then this one, the concentration of acetic acid is still 0.
Yep.
Okay.
Yep. There's none left. We've converted it all to acetate. And then it just stays acetate. We keep adding hydroxide, and so the hydroxide concentration goes up, but the acetate stays the same. It's not going anywhere. It's just staying, the same amount of it's going to be there. However much we started with, that's what's going to be left.
Okay, thank you.
Yeah, it's a tricky question, right? Yeah, I saw her ask that. It's like, man, yeah, it's kind of complicated. I had to think about it for a minute.
Thank you for explaining. That actually makes sense.
No problem. Yeah, there's a lot going on in that one. Because it's weird to think that, at the equivalence point, there is no more acetic acid. There's none. We have acetate, yes, but we don't have any more acetic acid left. And we can tell because the pH is no longer acidic, it's basic now. And so it's not an acid anymore. So now we have an excess of base. So all the acid is gone. The protons from the acetic acid have all been converted to water, and the acetic acid has all been used up, been converted to acetate. So there's no more left. There's no acids at all. It's all basic now. And so the pH goes up and up and up and up and up. All right, any other questions before we call it a day? Anybody have any questions about the third one, the third table? We went over it a little bit at the beginning. Does anyone still have questions about it?
I have a question about like the first table, just
Okay.
that's how for the parts of the data table where it's asking for the moles of sodium hydroxide delivered and the moles of acetic acid in the sample. Yeah, I'm just not really sure what type of equation to use for those ones.
All right, so
Yeah.
let's go back to the example I had the reaction that Roger did. So he had 4.84 grams of vinegar. And then we converted that to a volume using the density. I think that was 4.81 mils. So the initial, the volume of sodium hydroxide we delivered was 4.2. Then we went from 10.0 to 5.8. So that was 4.2 mils. So we know that the concentration of the sodium hydroxide is 1 molar. So 1 mole for every liter. So we delivered 4.2 mils. That's 0.0042 liters. 1 mole per liter, it's that many moles. So the moles we delivered was 0.0042. So what's the relationship between moles of acid and moles of base in this reaction? Because we need to write a balanced equation. What's the balanced equation?
It's like that one that you wrote down earlier, right?
It is.
Yeah.
So here's this is acetic acid and plus sodium hydroxide. So these are the reactants. What are my products going to be?
Products will be water and CH3, COO,
Yeah, acetate plus sodium. So sodium acetate, right. So, and that is a balanced equation. I have 1 mole of sodium. I have 1 mole of acetate. Yeah, so that's a balanced equation. So what's my molar relationship between acid and base in this reaction?
Should be a 1-to-1 ratio.
Exactly. So if I have 0.0042 moles of sodium hydroxide, how many moles of acetic acid do I have?
1. Wait.
No, if I have 0.0042 moles of base, how many moles of acetic acid do I have?
Oh, then you have 0.0042
Same number.
moles.
Exactly. Oops. Don't want to write that big. So 0.0042 moles of acetic acid. Now I convert that to mass, and my mass is that many moles times, I think it's 60.052 grams per mole. And so that is 0.42 times 60.052. So that's 0.252 grams. And my molarity is this many moles, so 0.0042 moles in what? What's my volume?
In liter, no, wait. Yeah, like
My volume for a vinegar in this, in sample 1 here. What did I figure the volume was?
it'll be, for this would be 4.81 milliliters.
That's right, exactly. Which is also 0.00481 liters, right? Just divide it by 1,000 to go from milliliters to liters. So my molarity is 0.0042 moles over 0.00481 liters. So that is 0.873 molar. Now, this is where the tricky part is. The percent mass of acetic acid. Now that one is a little harder to do because we want a mass percent of acetic acid. So what does that mean? That means what is the mass of acetic acid divided by the mass of the solution. That's what percent mass means. So percent, so what's the mass of the solute over the mass of the solution? That's percent mass, right? So how am I going to go from this, my molarity, to this? Think of what molar means. What's the actual definition of molar?
The definition of molar?
Mm-hmm. What is molar defined as? So that's going to help us do this problem.
Is that like the mole mass of something?
What does molar mean? What is it? If something is 1 molar, what does that even mean? How do we define molar? It needs to measure something, but what? The concentration, right?
Concentration?
Yeah, molar means concentration. Molarity of something gives you the concentration of something. But what are the units?
Yeah, the molarity, yeah.
Yeah. But what are the units we use?
M?
Right, capital M. What does that mean though? How do we calculate molarity? We divide something by something else.
Like you do moles over volume?
That's right. That's right. We divide moles by what?
Volume?
What volume? It's a very specific volume.
Volume of the solution?
Right, the volume of the solution. What volume of solution? Like a quart, a gallon, how much volume? A pint, a cup, teaspoon? What volume do we use?
Use a liter?
A liter, exactly. It's the metric unit of mass, is liter. Then everything else is derived from that. So it's moles over liters. So we're going to use that to figure out our percent mass. How? Because I'm going to convert moles to mass, and I'm going to convert liters to mass. Well, how are you going to do that, you might ask? Well, I know what the concentration of my solution is. It is 0.873. Well, what does that mean? It means it has 0.873 moles in 1 liter of solution, right? That's the very definition of molar. All I need to do now is convert this to mass and convert that to mass. So I can convert 0.873 moles of acetic acid to mass. I know how to do that. And I can convert 1 liter of solution to a mass. How am I going to do that? I mean, I can use the molar mass of acetic acid to go from moles to grams on the top. So I'll use the molar mass to change my numerator to mass. How am I going to change the denominator to mass? How am I going to go from, what's the relationship between volume and mass?
Not sure about that first part, but I think I have to use the density of...
Bingo, exactly. That's the relationship between mass and volume, is the density. So if we have the density and the volume, we can just change that to mass. So what's the density?
The density is 1.005 grams per milliliter.
Exactly. 1.005 grams per milliliter. So if I have 1,000 milliliters, how many grams is that?
1,000 milliliters. So that would be, but using this density would have 1,005 grams.
Bingo, exactly. So I can convert the denominator from 1 liter, and I can change that to 1,005. Now, how am I going to change my 0.875 moles to grams? How do I do that?
You would
So I have
use
0.873 moles of acetic acid.
You would use the 1 mole of acetic acid.
Yep.
Yeah.
So I'm going to multiply that by, I want to get rid of moles and I want to change it to grams, right? So I'm going to put moles on the bottom and the molar mass of acetic acid on the top. And the molar mass of acetic acid is 60.052 grams per mole. So moles of acetic acid are gone and I'm left with grams of acetic acid in the numerator and grams of solution in the denominator. And that's precisely what I want because that is percent mass. That's my mass of the solute, which is my acetic acid, divided by the mass of the solution, which is the denominator. So when I do that, see, times 60.052. So I've got 52.44 grams of acetic acid divided by 1,005 grams of solution. And I get 0.052. Multiply it by 100, 5.2%, which is pretty good. That's pretty close to 5. You should get, your answer should be pretty close to 5.
Yeah, I just calculated. Mine was like 4.95.
Man,
Just-
perfect. That's even closer.
Okay, yeah, that really helped me a lot. Thank you very much.
Yeah, no problem, no problem. Yeah, see, your data's better than you thought. Any other questions before we go? Man, it's getting late today. We filled up the time. That's good. Oh, let me check the chat. What's going on? Oh, values in table 3. Yes, copy that. And then you fill in the table. Everything that isn't grayed out, you can fill in. So let me just clear this. So yeah, table 3. So the volume, these are 3 different titrations of acetic acid with sodium hydroxide. So it gives you the initial pH to start with. Each one of them is 21.05 mils of acetic acid. And then it tells you what the initial volume of NaOH was. This is the initial volume. This is the final volume. The difference is the total volume of sodium hydroxide. The concentration of sodium hydroxide, 0.1 molar. So figure out moles of hydroxide. That will give you moles of acetic acid. And then remember that halfway through the titration, so half of this volume, so at the midpoint, the burette read that. So take that volume, 9.5 minus 1.61, figure out how many moles of sodium hydroxide were present then, how many moles of acetic acid were present at that point, and then you use this formula to determine what the pKa is, because they give you what the pH was midway through. So you have the pH. You have then you calculate the concentration of A minus and the calculation of the acetic acid. Take the log of that, and then you calculate the pKa.